Yeah, Assalamualaikum warahmatullahi ta'ala wabarakatuh and a very good day. Again, my name is Hakim. I'm from a lecturer from Faculty of Ocean Engineering, Engineering Technology and Informatics, University Malaysia Terengganu. So welcome back to Fluid Mechanics KEJ3104. Right. So today we're going to learn about topic 2, the properties of fluid. Of course, I have shown you in the previous topic, in the topic 1 about the introduction, where you have learned a little bit information about who actually have caused you to learn about fluid mechanics and stuff, and also how the viscosity that have caused a bitumen to only have a drop of 8 drop of bitumen within in 70 years time. So that kind of visco properties that we're going to learn today together. So this is the outline where I'm going to show you how the volume expansion, how the density, how the temperature and pressure affect the density and so on. Okay. Right. So this is our objective, that we are going to work on the knowledge and basic properties of the fluids and continuum approximations. The most important part I'm going to stress out over here is about the viscosity over here, where how this viscosity going to affect the frictional effect, how it consequences on the fluid flows. Of course, we're also going to learn about a little bit on the capillary rise. I'm going to show you later what is capillary rise about. Okay. All right. Next is a little bit introduction about the property. We have about 3 type of property, where we have intensive, extensive, and specific properties. As you can see here, as we go down in deeper, we have more uh, properties involved in it lah. Okay, so some kind of characteristic come within the system, such as mass, volume, temperature, pressure, and density. Even we have viscosity as well. So a lot more than that. All right. Okay, so this is the continuum. You can read about it. What is continuum about? But it generally about a space with no jump of discontinuities, something like that. Okay. So this is the example of the seagull, how the length of its wings actually associated with the most flows. And if you can see here, it says that the seagulls in flight is ordered the magnitude larger than the mean free path of the air molecules. It has to do something with the molecules around here. Okay. Right. The next one, the third one is the density and specific gravity. So I think from your SPM, your O level, your A level previously, you have seen what is the density formula about. Density equal to mass divided by volume. Mass where is macam berat dan volume ni adalah macam meter cube. The volume lah, isi padu. Okay, the specific gravity is the volume. The density of, let's say, if you want to refer to air, it has to be in the ratio of the specific gravity itself to the water. Specific of the gravity of the water usually comes in 1,000. Okay, if you can see on the table here show that the specific gravity of substance at 20 degrees Celsius and the pressure of 1 atmospheric. Apa pressure at 1 atmospheric ni kat mana? Sekarang lah yang dekat kita hidup sekarang ni, in our room temperature, in your room, in your class, in UMT or in wherever you are now, at the sea level here, we are at 1 atmospheric. As you can see here, it has a different specific gravity. For water, the specific gravity value at this is 1 atmospheric. But for different substance over here, it has a different value. Okay, again, this table is quite famous actually among the chemical and mechanical engineering, also any chemical technologies. As you can see here, as the temperature increase, the density decrease. Same goes to the dynamic viscosity. It change, the value change, depends on the temperature, and sometimes depends on the pressure as well. But this one is water at atmospheric pressure. So when you boil the water, you may know the density of water is increase or decrease. When you boil the water to 100 and it's boiling here, what is the value of the density? Okay, so this is the ideal gas. This is the density of ideal gas. Okay. Normally the most famous equation comes from PV equal to nRT. Usually you have to remember this equation lah, because this is the ideal gas equation of state. It's quite the most simplest one. So it comes from the PV equal to RT, or P equal to rho equal to RT. So the derivations, you will get PV equal to nRT. As you can see, density, or we call it rho, equal to m over v that I've shown you in the previous slide. So and at the same time, the molar mass equal to mass divided by, not molar mass, mole here equal to molar mass divided by molecular weight. Or you can just simply put it capital M over there. So M equal to, here, M equal to N times with the molecular weight over here. So if you substitute it, if you substitute this inside here, so rho equal to N M divided by V, where you got the V here, M over V here equal to rho and stuff lah. Okay, so you can get here rho equal to M mass over volume, or equal to the mole times the molar mass divided by the volume. And this one can be, you can convert it back and put it here, and you got the rho equal to Pm over RT. So that is the derivation. Okay, next. Discard. Okay, so next is example of how we use the ideal gas equation. So in this example, it says calculate the density of methane gas at 100 C and 2 bar. Okay, bara A means absolute pressure. 2 bar absolute pressure. Okay, so it's given here for ideal gas. To find the density, this is what we got for the equation of the ideal gas. So it just simply move in. So P, we know the pressure we know here is 2 bar. The pressure we know is 2 bar. But bear in mind the unit. It's bar equal to 2 times 10 to the power of 5 Newton per meter square, or Pascal. Okay. And M here, molecular weight of methane. C, the molecular weight of carbon is 12. Of the hydrogen is 1, but times with 4. So you got 4. So 12 plus 4 equal to 16. And then what else? Divide by R. R is the constant. Bear in mind the unit. So sometimes it can be R can be expressed as 8.310 kilojoule per kilomole Kelvin. But here it has on divided by times with 1000, it becomes 8310 joule kilomole times with the temperature. Temperature has to be in Kelvin. So it given 100 plus 273. So you got here 1.032 kilogram per meter cube. Okay. All right. So the next one is determine the density, specific gravity, and mass of air in room. Jadi dia nak tahu determine the density, specific gravity, and mass udara di dalam, katalah bilik tu sebesar ni, 4 darab 6 darab dengan 5. Nak tahu jumlah berat dan density udara ni adalah air. Ni dia boleh air ni di dalam. Okay, the first one, soalan dia adalah determine the density. Yang kedua dia nak specific gravity. Yang ketiga dia nak adalah mass. Okay, so what is given to us as volume? Volume given 4 times 5 times 6 meter. Okay, equal to, I think it's 100 meter cube. What else given? What else is given? Pressure is given. Pressure equal to 100 kilopascal. What else is given? Temperature. Temperature is given 25 degrees C, or you can plus or equal to 298 Kelvin. Okay, and what else given? What else is given? So R here. Okay, R for air, 0.287. Okay, so the first of all, the first equation is given to find the density. So the formula P equal to rho R T. Okay, so we want to know the P here. So you rearrange the equation, rho equal to P over R T. So here, you know P is 100 divided by R is 0.287 times with 298 equal to 1.17 kilogram per meter cube. Okay, that is the first one. Okay, so B it says specific gravity. So specific gravity Sg equal to rho of air divided by rho of water. Okay, rho of air we know here is 1.17 divided by 1000 equal to 0.0017. That is for specific gravity. Okay. Okay, for the next one, okay, I'll add a new slide. So the next one, it says to calculate the what is it? The next one is the mass. We want to calculate the mass. So as we know here, rho equal to m over v. We want to know the mass. So m equal to rho times with v. So we know rho here is, the density here is 1.17 times with the 4 times 5 times 6, which is 1.17 times 120 equal to 140 kilogram. So 140 kilogram is the mass of the air inside a room that has the dimension of 4 times 6 times 5 meter. Okay, so that's the first one. Okay, the next one is the vapor pressure and cavitation. Okay, I'll show you a little bit what is cavitation later. However, for this vapor pressure, we have T set, which is the temperature at saturation. At saturation temperature, you call it. P set is pressure at saturation, and vapor pressure, and we also partial pressure. You can read what is the information about here. If you don't understand, you may ask me later. Okay. Okay, the next one is vapor pressure and cavitation again. So as you can see here, saturation of vapor pressure of water at various temperature over here given on the table here. As you can see, as the temperature rising, makin naik temperature ni, the saturation pressure also increases. Okay, so this is another kind of properties for the fluids. Okay, so another boring stuff here is energy and specific heat. So this is actually what we call it a subsection of the total energy. So adding up the internal energy, kinetic energy, potential energy, and another kind of energy would be the total energy. That's the summary of the energy and specific heat. Okay, so as I explained to you before, enthalpy and energy of flowing fluid, it depends on the here U P times V. For the enthalpy, you can have this one. For energy of flowing fluid here, so you can have the summation of the kinetic energy, potential energy, and the height and everything. Okay. I'm not going to focus on that yet because we're going to learn more on the flowing fluid in topic 3 and more. So this is the specific heat. As you can see here, they have a CV, specific heat volume, specific heat pressure. Yes, for different value over here. Okay, the next one is compressibility and expansion. So as you can see here, coefficient of volume, expansion. Okay, guys. So the number 9, the outline number 9, what we're gonna learn next is compressibility and expansion. So ada dua benda lah, compressibility and expansion. Compress ni maksudnya you are compressing them, makin kecil lah. Expand selalunya kita expand dia makin besar, dia akan makin besar. Okay, kita tengok yang mula-mula sekali expansion. Expansion ni kita guna unit ataupun simbol dia sebagai beta lah. Okay, so rearrange semua ni. Usually kalau dia tanya equation of expansion, selalunya equation dia akan bermula dengan the difference of rho, which means the density, equal to negative coefficient of volume expansion equal to beta times the rho, which is the density, times with the difference of temperature. So that would be the expansion. The next one, the compressibility. Compress, yang ni makin kecil. So selalunya formula dia adalah delta P, delta rho of the change of density equal to, it represent by alpha rho delta P. Delta P, delta of change in pressure. Okay, so that would be the formula for compressibility and expansion. Okay. Just gonna keep. Okay, so this is the kind of the formula that will be rearranged and derivation for your more information about the combined effect of pressure and temperature and so on. However, I want you to focus on this chart where, if you can see here, the coefficient volume of expansion is increased as the temperature increase. Okay. Right. So the next one, let's do a little bit example. Okay. So from the question here, it given that consider the water initially at 20 degrees Celsius and 1 atmospheric. Okay, yang paling normal sekali lah maksudnya. Temperature air 20 dengan pressure 1 atmospheric. Determine the final density of water. Maksudnya yang A ni dia nak, A ni dia kata heated. Heated daripada berapa? Asalnya 20 kan? Daripada 20 degree Celsius kepada 250 degree Celsius at 1 atmospheric pressure. Okay, jadi maksudnya bila dia heated, dia menerima tenaga, maksudnya dia akan expand. Ingat balik apa formula of expansion. Jadi formula dia adalah delta rho, the change of density equal to negative coefficient of expansion times with the density times with the delta temperature. Delta, the change of temperature. Okay. Jadi daripada sini kita dah boleh cari. Mula-mula kita nak tahu. Kita dah tahu. Okay, daripada graf ni, kita kena determine. Nak tukar color. Kita boleh determine what is the value of volume of expansion at the respective temperature, for example. Okay, so given at the beginning, the temperature is 20 degree Celsius, and then it goes to 50 degree Celsius. Okay. Alright. So first of all, we need to know how much actually the temperature increase. So we need to know the average value of the temperature increase. So 20 plus 50 divided by 2 equal to 35. So from the 35 degrees Celsius here, we may find the coefficient of expansion. Okay, so here equal to negative 0.0337 times 10 to the power of negative 3 times with, you have to find the rho for the temperature at 20 using the table given in the previous one, which is, in this case, is 998 times with the change of temperature. Change of temperature is 30 times with 30. So you will get the value here is negative 10. You get the negative 10. Okay, the next one. The next one, B, is it says that if it compress 200 compress from 1 atm to 100 atmospheric. 99 naik. Naik 99. Jadi dia kata yang ni bila dia compress kita kena guna formula compressibility. Formula compressibility. So formula compressibility equal to rho 2 minus rho 1 or equal to delta rho equal to alpha rho times with the delta P. Delta P. Yang tadi tu delta T, ni delta P. The change of pressure pula. Jadi rho 2 minus rho 1 equal to 4 times 8 times 10 to the power negative 5 times 998 times with the 100 minus 1. So you will get 4.74 plus the delta P, delta rho. So the answer for the rho 2 equal to 4.74 plus 998. So you will get the answer here. Okay. So the next one is the speed of sound. So for ideal gas, the speed of sound equal to C equal to the square root of K times RT. Okay. So that will be the formula. And K usually given in the equation. That is the specific heat ratio. Okay. So this is the sound, the speed of sound and Mach number. This is the Mach or Mach. You can call Mach or Mach number equal to MA equal to V divided by C. The velocity divided by the C. See where you get the here. So this is the Mach number from NASA. So the Mach number, if it's less than 1.0, it's about the, for the small, not small airplane, but the commercial aeroplane. But here, what we got is Mach number is more than 5. It's about the hypersonic. Okay, so from the example 2.4, it says air enters a diffuser shown in figure 2.22 dalam gambar ni. Jadi at speed of 200 meter per second and then determine the speed of sound. Okay, pergi balik dekat formula ni, kita tengok speed of sound. Jadi dia nak tahu speed of sound ni. Speed of sound C. So formula dia square root of K times R times C. Okay, so A C equal to K times R times T. Okay. For R is given 0.287 for the ideal gas. So we can directly, is given as 30C, the K specific heat ratio is 1:4. Quite straightforward. 1.4 times 0.287. Okay, times with the 273 plus 30, which is 303 in Kelvin. Bear in mind about the unit, you have to times with the 1000 to get the. You have to bear in mind about changing the kilopascal per meter cube into the meter per second. So you got here 349 meter per second. Okay. Okay, and then the second question is find the mass number at the diffuser inlet when the air temperature is 30. Dia nak yang B ni adalah mass number. MA, we know the equation equal to V over C. Jadi kita tahu V adalah 20, C kita tahu 349 equal to 0.573 and MA number here is less than 1. So it's had, you can see here, subsonic. So the next one is the viscosity and drag force. Okay, as you can see here, the drag force is not equal, but the drag force exists even in air or water. It says here a fluid moving relative to a body exerts a drag force on the body, partly because of the friction caused by the viscosity. Kalau tak ada friction, tak ada viscosity, friction tak ada, lajulah ikan dengan eagle ni dia terbang without friction. Okay, the next one is kinematic viscosity. So given the kinematic viscosity for gases, this is the formula. For liquids, this is the formula. Okay, so this is boring stuff. You want to read, you can read by yourself. What I want to do is we have to learn about more on problem-based learning. So as you can see in the photo here is the viscometer. Is the viscometer. Yang ni dia ambil crossover. You can see this is, kalau tengok daripada bawah cross dia, inilah rupa dia sebagai cross section. So formula untuk calculate the kinematic viscosity, kinematic viscosity equal to 4 times pi square times R is the R here, cube times with the n equal to the revolution number per unit sebab benda ni dia pusing. Times with the L, the length of the cylinder, and then times with the L here. Okay, L here. Okay, the next one is the viscosity, determining the viscosity of a fluid using the viscometer. The viscosity of fluid is to be measured by a viscometer constructed of 240 cm long concentrated cylinders. The outer diameter of the inner cylinder is 12 cm. And the gap between the two cylinders is 0.15 cm. The inner cylinder is rotated at 300 rpm. And the torque is measured to be 1.8 Newton meter. Okay, so let's get back to the equation here. T equal to, kita tengok balik ni Kita tengok balik equation ni, saya rearrange balik kat sini. T torque equal to the viscosity times with the 4 pi square times with the R cube times with the N naught L divided by L. Okay, so if we rearrange equation, so because we want to the viscosity is measured, determine the viscosity. So the question is want to determine the viscosity. We want to find the viscosity. So rearrange the equation. That would be TL divided by 4 times pi square times R cube times with the N naught times with the L. Okay. So here let's gather the information we got. So given in the equation T equal to 1.89 Newton meter. Yeah. Okay. And then what else we have? L L is given here 0.15 cm. L here. L here is given 1.5 cm. Okay. And then next what we have R. R is given here inner the diameter. Diameter is given 12 cm. So 12 cm, which means 12 divided by 2 to find the diameter, which is 6 cm. And then what else we have? We have the N naught is 300 RPM. And then else we have the length. Length is 40 cm. Okay, so that's all the equation given. So as now we have everything, we can substitute it to find the viscosity. So equal here 1.8 times with 0.0015 because the cm converted into meter divide by 4 times pi square times with the r is 6 cm convert into meter 0.006 meter cube times with 300 RPM. You have to convert it to second. Convert it to second. 300 radius per minute. So you want to know how much radius per second. You have to divide by 60. So you got how many seconds over there. And then L is 40 cm or equal to 0.4 meter. So here, compute the answer. You will get 0.158 Newton second per meter square. Okay, so that will be the example 2.5. Next is the surface tension. Is you can see from the photo here, boleh tengok dekat gambar ni, macam mana bugs ni, serangga ni, dia berada di atas air dan terapung dengan menggunakan surface tension. Dan juga clip dekat sini dia terapung disebabkan oleh surface tension. So, this is the equation for the surface tension. As you can see, the surface tension on here is actually different for different different fluids, and it's also different for different temperature for water. Okay, the next one, the last one I guess is the capillary effect. Kita dah tengok lah sebelum ni capillary, kalau mercury ni, kalau mercury capillary effect dia selalunya ke dalam. Kalau water dia ke atas. Jadi capillary rise punya formula adalah H equal to 2 tau S divided by rho GR times cos theta ataupun mu. Okay. So, kita buat lagi satu quite simple example. So it says here 0.6 mm diameter glass tube is inserted into water at 20 degrees C in a cup. Okay, determine the capillary rise. Determine the capillary rise. So kita tengok balik formula capillary rise adalah ni. Okay, kita bawa datang sini. Okay, H equal to 2 S times the cos theta divided by rho GR. Okay, so that would be the formula. Okay, so it's given at 20 degrees Celsius and the tau S is 0.073. Go back to the, how do I go back? Okay, at 20 C, the tau S is 0.073. Okay, so we just may simply, okay, one information is if we're using cup or glass, you can consider the theta equal to 0 degrees Celsius. Okay. Okay, so now we can simply substitute H equal to 2 tau S equal to 0.073 times with the cos 0 degree divide by, this is rho for water is 1000, density for water is 1000, times the gravity is 9.81 times with R. times with the r is the r is given? Yes, the radius. So the given is diameter. So we have to divide by 2. Divide by 2 will be radius times and divide this to 1000 to change it to meters. So you will get 0.0496 centimeter or equal to 5 centimeter. Okay, quite simple and straightforward. Okay, so for example 2.7, I'm not planning to teach you, but if you are interested, you may read about the example 2.37. Okay, thanks for watching. Thank you. Next is the tutorial for question 1. You may do the tutorial question 1, 2, 3, 4, and 5, and 6. The answer is given at the bottom of the question, and when we may discuss in the next session. Thank you.